Hello, everyone, and welcome to our webinar today. My name is Paul Bemis, and I am the president of Applied Math Modeling. Today, we're going to be discussing dispersion analysis for a hospital. This happens to be a VA hospital, and we've done a number of these analysis for VA hospitals. It appears that they're quite interested in seeing the impact of dispersion of pollutants from a variety of things into the fresh air intakes. Just a note about the company, in case you don't know us. I think most of you do. We're founded in 2008, so we've been here now 18 years. We came from the Ansys Corporation, where I worked for many years, and we are responsible for development, sales, and support of the CoolSim application, which is primarily focused on data center design optimization. However, we do other things as well. We're CFD modeling people, and we model buildings of all kinds and properties associated with those buildings of all kinds. So in this case, it happens to be a hospital. We are, as I mentioned, experts in the field of CFD, as well as engineering simulation in general, but focused on CFD. So this particular hospital that we took a look at is a VA hospital located in Florida. And the issue was that they're planning to install new air handlers, shown over here in green. So there's a couple of air handlers they're going to put on, and they're concerned about the surface and what would happen as wind traveled over. Would these recirculate? Would they pick up intake from adjacent devices, most notably these devices, which are diesel generators over here in red. So they wanted to understand the impact of wind change on the modifications they were making to the building. And temporary generators are going to be there. And the question they have, of course, is does the exhaust from the generators infiltrate the air intakes? And if so, how much? Now, the question of whether or not they do can be predicted, and the quantity can be predicted using CFD under a prevailing wind. And we're going to show you how that is done. So the way that that is done is to define the exhausts and the location of the vehicles. These are trucks parked, idling. And so there's hazardous gas coming out of these. There's also some kind of hazardous gas coming out of a device over here. Don't know what that is. These are hospitals, so it could be anything, but they don't want that to get into the intakes either. And then over here, they have some generators, and the generators could cause issues as well. The primary objective is to determine the concentration of these gases into the air handlers. And temperature is sometimes interesting as well to this set of customers. Not always, but sometimes it is of interest as well. So we can do massless particles is how we model it. Particle dispersion method is what we use. And we take a look at these particles and see how many are getting into the intakes. And then a distribution plot is created to identify areas of high concentration. And then we compare it against the ASHRAE recommended standards for this kind of material to determine if the concentrations are too high. So that's the methodology. So first you must set up the building. Often the building can come from a variety of sources. If it's CAD, if you have a CAD model of building, that's great. We've gotten pretty good at being able to take a Google Earth image and transcribe it into geometry as well. So even a location of a building is good if someone can identify where the inlets and outlets are. And most importantly, we need to know what the magnitude of these devices are. So here we have inlets and outlets. These are exhausts. And so there's air coming out. We need to know the direction, of course, and we need to know the magnitude. What is the total amount of air coming out of them in cubic feet per minute or some other method. That's an American, that's English, cubic feet per minute, but it could be cubic meters per second or cubic meters per minute. We don't really care. We need to know flow temperature sometimes. Sometimes flow temperature is important if you're worried about, in the case of thermal contamination. This is very evident and important for data centers because they stack the air handlers, the chillers very close together, and we can have thermal contamination from an upwind chiller to a downwind chiller. In this case, generally it's not thermal. Here it's particulate. NOx and CO are the two that come up the most often. Now, for generators, what we do is we make some assumptions about their operation. The generator is really just a diesel device, so it's burning diesel. It's got an outlet. It's got an exhaust stack, generally running at about 900. It's got a heat exchanger, so we have a radiator inlet, radiator outlet, and the stack itself. Those are the three components. The reason you want to consider the inlet is because it creates a low pressure and can disturb the air around it, causing some different kinds of effects to happen. The outlet here, this 900 degree, is important for thermal because that's obviously a thermal source right there that you may have issues with. The radiator outlet, not a big deal, but it's a higher CFM. So there's more of it, but temperatures are quite reasonable. That's a fairly low number for radiator outlets. They tend to run in the range of 150 to 200 C. Now the idling truck over here, we simply modeled as a temperature outlet source, of course, and also a flow rate with particulate. And we got the specifications, we'll show you in a moment, from literature we found on the internet. In this case, wind is going to be 11 miles an hour from the south at a temperature of 82 degrees. Wind direction and speed is generally determined from a windrose. If you're not aware of a windrose, it is a round circle. I didn't put one in here to show one to you, but it shows you the history of wind direction and magnitude over a period of time. It can give you an indication of the prevailing wind and its magnitude and the frequency at which it occurs from a windrose. So we use that a lot to determine wind direction and wind speed. In this case, it's coming straight at the building. This is probably the dominant wind direction and the dominant wind speed. So we have this pressure plot, of course. There's the pressure. Of course, there's the air is banging right into this flat surface of the building and creating a pressure field. That pressure field will disturb the flow here, of course. The air will tend to bang into this, pressure changes, of course, because the velocity is changing. And resulting temperature contours, really no effect here in terms of temperature. Some little tiny effect of thermal in one section, but really the generator exhaust has no real observable thermal impact. So we're looking at output now. These are resulting temperature contours that can be derived. As well, the effect of flow from the exhaust on those diesel generators is really negligible as well. These are questions you want to typically have answered before you proceed. So what this tool allows you to do, or the modeling allows you to do, is make sure your designs are going to be satisfactory before you build them. That's primarily the goal of this kind of modeling, whether it's CFD or finite element. It is to predict the performance before you deploy it to ensure that it will work once you're in the construction stage. These are pathlines. You can understand here the air is coming from this direction, banging into the building and then wrapping around. It will cause some recirculation on this backside. As you can see here, that's the low pressure side. Over here, this is the high pressure side. So wind bangs into it, slows down, wraps around the edges. You can see it picking up that air handler right there and wrapping it around and moving it off to the back. So the air handler 1, the dominant intake is coming from the back side of the building. So these are paths of intake. These are path lines. You can see the arrow direction, path lines of air intake to the air handler. You can do them in either direction. We can do path lines of exhaust and path lines of intake. These are inlet path lines, and you can see those arrows are pointing to show the air coming and banging into the building and then wrapping. Because again, this is the low pressure side. So that's where the air is going to be pulled from for this particular air handler. And then, of course, here you have path lines of air coming in as well. Here it comes, and it bangs into that building and wraps down around and comes into the air handler number two and number three. For this air handler over here on the east side, air is coming from the back and wrapping around. So what the model does is it allows you to see where the air is coming from and where the air is going to. CFD allows you to visualize airflow quite easily. And so the emission rates here were assumed to be a certain level. These were drawn from literature. So diesel engines exhaust at approximately 3.8 grams per second of NOx and 0.203 grams per second of CO, carbon monoxide. And so that is the generation rate. We obtain that again from diesel generator data that we find related to these kinds of systems. And then the vehicle itself, truck diesel engines, you can look that information up as well. And you put in the amount of NOx and CO coming out of this device as well. So the emission rate assumptions are drawn from the literature that we find related to this kind of device at this RPM. RPM does make a difference here. These are idling, so they're fairly low. These are the diesel generators. That data can be obtained as well. 0.51 grams per second of NOx and 0.026 grams of CO, monoxide, coming out of those. And then we take a look at concentration. So here we're taking a look at NOx concentration with and without a diesel exhaust filter on it. So the exhaust fluid or DEF fluid that's a filter system. It's injected into the exhaust and it improves the catalyst reduction process and reduces the amount of NOx. Modern cars have this as well. If any of you have a diesel automobile, you know you have to add this fluid because that is the element that helps catalyze the diesel exhaust and reduce the NOx. In this case, we did it both ways because we weren't sure whether the diesel generator had the DEF model or not. So we looked at it in both directions. This is concentration without the DEF model attached. And here's the monoxide concentration under that condition as well. And the concentration values are well within the acceptable ASHRAE. We're talking here about ASHRAE 62.1, which is the only specification there is that really deals with air quality. That specification covers both internal and external environments. We use it a lot inside as well for pathogen mitigation. We model interior pathogen transmission and mitigation. We did a lot of that during COVID. Here we're looking at the external flow, and 62.1 is still the spec we use to take a look at that. So here's the report for engine emissions. This is with the diesel exhaust fluid model, and this is without the diesel exhaust fluid model. The existing generators are shown here with their exhausts, and from idling trucks are here as well. So we have total concentration. We produce both grams per second is the NOx amount is inhaled into the intakes. Take 1, 2, 3, the ones we're worried about, and 1, 2, 3, 4, and then the concentrations of NOx that are resulting. You can see these numbers are really quite low. 7 times 10 to the minus 4th, 48 parts per billion. We compare this against the ASHRAE 62.1 standard, which says that it has a time period. Within an hour, per hour, within a 1 hour period, there shall be no more than 100 parts per billion for concentration. 1 hour daily maximum concentration. And you can see here that even, we're in pretty good shape on that. This is NOx and O2, 100 ppb, and the primary and secondary should be within over a year period of 53 parts per billion it's the annual mean. Okay, so you compare that to what we're seeing, we're below that number with the DEF model. We get a little bit up on closer to that model or that number on the intakes 3 and 4 when you do not have the DEF model in place, which would not surprise you, of course, because it's putting more particulate, more of that gas into the atmosphere. And here's the relative carbon monoxide numbers. Again, the gas generation numbers here, temporary exhaust. Here's the exhaust from the idling trucks and the relative air intake. So we're taking all of these things that are running right now and then projecting them to see what those intakes look like using something called scalar mixing. So for carbon monoxide over an 8-hour period, you want less than 9 ppm, 9 or less. 35 over a 1 hour period, you can see we're well below that. So that's how we do it. On the building itself, we're looking at particle report here for exhaust. These are analytical calculations that we did. Number of particles injected were 2,500 from the rooftop outlets and louvers. And these intakes, of course, are negative because they're pulling air in. So we're looking at the percentage of particles entering the air handlers themselves, and then its concentration of air volume on those inlets. Okay, so if we assume 2,500 particles per second were emitted on the rooftop, the total amount ingested is 0.614%, or a 4% concentration. And the highest individual concentration represents a concentration of 2%. So again, very low, but this is under a wind condition. It may change with other wind conditions, but under this wind condition, these are the outputs you get, and you're able to predict with fairly good accuracy how that's going to occur. So that's really the conclusion here. We were able to take a building, put the inlets and outlets on it, put diesel generators in the environment, run them, and then take a look at the worst case condition. So the worst case condition in this particular scenario for NOx on inlet O3, we can even predict which one is the highest, as a value of 87. That does assume the diesel exhaust filter is working, installed and working correctly. The specification is 100. The carbon monoxide is worst case 0.0145 parts per million, well below the 35 parts per million requirement from ASHRAE. So based on that assumption, the amount of particle ingested for the buildings is not significant enough to cause any kind of human issues, human health concerns. We don't know the chemical composition, so particle count is what we use to predict the transmission. But the worst case scenario shows a concentration of 2% of the total volume. So it does depend what these things are. You know, if they're radioactive particles, the 2% might be of concern. And we don't always know exactly what's coming out of the building because, and quite frankly, I'm not sure anybody does. So what we do in this case is make an assumption of volume, particles in this case, and then take a look at the worst case situation of concentration on that air handler. 2% is what we would see if the particle count was 2,500. So it gives you a feel. It may not be perfect, but it gives you a feel for how much impact the emission would have on the building itself, on the total volume. So this is the kind of work we do. It is not a data center specific presentation that I'm doing today. It's more related to general buildings. Data centers are buildings. So in fact, it is a building. And here it's just we're looking at something a little bit different. In data center applications, sometimes we are asked the same question. What is the NOx infiltration, the carbon monoxide infiltration into the intakes of the building? We are sometimes asked that question. It is not common because generally speaking, that's not an issue. It's more a concern about thermal contamination from one air handler to another. But we do model it and we can predict it for data centers or for buildings like this. This one happens to be a hospital. It doesn't have to be a hospital. This concern should be studied and understood, I think, on all commercial buildings. If you have fresh air intakes, we've run into many situations where fresh air intakes are causing issues. We worked on and I reviewed it in one of the earlier webinars. Let me go back to the geometry here for a moment. Very, very similar geometry. It was a casino. And with this section right here was a high rise where all the rooms existed. And down here was the gaming area. And on the rooftop were what they called grease hogs. They were devices pulling the smoke out of the casino area because smoking was allowed in this casino area. I think smoking isn't allowed in casinos in general. So they have to get the smoke out, and also they have to vent the kitchens, a lot of food being cooked. And what was happening, as you can imagine, is this smell was coming up and infiltrating these rooms. These rooms are very expensive, and to have the fresh air intake pull in the smell of a greasy burger was not desirable to the operators. So we were first able to predict the concentration of, in this case, smell in the casino, and then work on ways to mitigate it by getting it out of there or changing the devices so that they emit less. So it doesn't always have to be NOx and CO. It can also be just smell. But if you know where it's coming from, you can model its path through the air and its concentration to air intakes, wherever they may be. So I wanted to point out to you that although this is a hospital, and we do quite a few of these, my customer here, Dustin Brand, is with us today from CruxCon. At least it was CruxCon when we did this particular model. But we do see it. We do see the VA doing quite a few of these. We also see other buildings. In the case I mentioned, a casino. But we see other situations where this kind of modeling is important to understand how to make adjustments to mitigate either a smell or a pathogen. Pathogen mitigation is the same way. That's concentration of the pathogen, same exact idea. Or in this case, carbon monoxide and NOx. So that's really what we had today. I wanted to just show it to you, not an extensive presentation today, but I wanted to show you how that was done, and be willing to take any questions here. If anyone has any, just type them into the chat if you have any questions, and we can answer them for you. Okay, I don't think there are any questions at this point, so I'm going to close the webinar for today. Thank you for attending. And for those of you who missed it, we did make a recording of it and we will be posting it. Thank you very much.